So, good afternoon, everybody. It's a pleasure to be here again to give my next Gresham lecture and the final one of this academic year. So, I'm going to tackle today the dark aspects of the universe, the dark matter in the universe, really. Okay, so we do have an issue here in our understanding of the universe. An awful lot of it we do not see. Now, this is a fascinating question, actually. It's attracted attention in many other areas. Here's an example from the field of art, where a well-known American artist did a series of dark paintings. The things that vary are the frames, of course, but there's a close-up. And, you know, dark matters. There you go. Okay, so let me take you through the beginnings of this problem in our understanding of the universe. I suppose you can really go back to the 1920s and blame the beginnings of cosmology, or the modern cosmology, where Hubble first discovered, with the aid of Georges Lemaitre, who also independently discovered this, the expansion of the universe as measured by the recession of the galaxies. And so, with Einstein joining in the argument, it soon became clear that the universe was indeed, space was expanding, but there was a countervailing force due to matter to balance this expansion to some extent. The exact extent wasn't known, but it was clear there had to be an awful lot of matter in the universe, otherwise the expansion would make no sense. That is, the universe could not be too far away from a state in which, you know, expansion was balanced by the attractive force of gravity from matter. Okay, and so this was sort of the motivation for beginning to think about matter as being dark, some of it as being dark, because it was clear that if you wanted to understand how rapidly the universe expands in its future, you know, if there was a lot of matter, it would reach a maximum size and recollapse to a big crunch in the future. And if there was relatively little matter, then it would expand forever and ever. And so this is an important, issue. What is the future of the universe? And so the amount of matter became critical, and it was clear there was not enough matter that we could see directly to cause this future big crunch. And so if this did happen, it would have to be somewhat dark. Okay, so this was, the 1930s. This discussion went on for 20, 30 years. More actually, until probably it took to 1990 before we finally got modern measurements in cosmology, and it became clear over the past decade or two that there is an awful lot of matter out there that we simply cannot see but must be there, is inferred to be there, just to explain the overall structure of the universe. And this is the budget for the expanding universe. This is the stuff that we're made of, the ordinary matter. We're only 5% of the universe. I mean, it's really amazing to think that we're such an insignificant fraction. It's important, obviously, it's critical, otherwise, our planets and stars wouldn't be here, but they're the ordinary matter. Nevertheless, there's 5 times as much dark matter. And there's even more dark energy, which I'm not going to talk about because that's something that has its origins in the origin of the Big Bang and is a whole other issue. But I'm going to focus today on the dark matter, which is a much more concrete thing because this surrounds us everywhere and is inside our galaxy. It's inside in the Earth, throughout the Earth, everywhere. There is dark matter, we think. And to give you some feeling for the first place to look for dark matter, because it's clear that the stuff that we see shining, the galaxies, is not enough to explain the global mass budget of the universe. There is more that's needed. And so the first obvious place to put this extra matter is in this dark and invisible halo about our galaxy. And so there are occasional stars spotted through this, but you'll notice the density of stars in the center is very intense. But out here, most of the matter, 90% of the mass of our galaxy, is thought to be invisible. Okay, so this is a presumption, and this is what we most likely need to understand the global budget of the universe. But what I want to talk about today is how we measure this. Why are we so certain this stuff is out there? And what are we doing to try and actually detect it directly? Okay, that's the issue. Until we actually find it, we're never going to be totally convinced that it's real. Okay, so let me then tell you how one can try to measure this dark matter, the stuff that is around our Milky Way, where much of it must be, if it exists at all. Okay, and we conjecture that it does exist. So this is what you do. This is almost the only equation I'm going to show you today, but just to give you some feeling for this, you measure a galaxy full of stars like the Milky Way. It's spinning, it's rotating. And the stars have some speed. And from the speed of those stars, you can infer the mass that's contained within the orbits of those stars. That's basically what controls the speeds of stars, just as the speed of the Earth around in its orbit is controlled by the mass of the sun. Okay? And the further out you go in the solar system, the slower the planets are orbiting, because the gravity field is weaker. And so that's what you would expect in the galaxy. The gravity field should get weaker, the speeds of stars should get slower, the further out you go. Okay, so that's the underlying essential theory that comes from understanding of gravity. Gravity determines the speeds of stars in orbits. The more gravity there is, the faster they must be going in orbit to counterbalance that gravity. The weaker the gravity, the slower they need to go. So that's sort of the story. So how do astronomers then go about entering this challenge to see if there's any dark matter out there? So it began with these two astronomers, Vera Rubin and Mort Roberts, in the 1950s, and they did detailed studies of a nearby galaxy in Andromeda, one you could just barely see with the naked eye, a very faint patch of light in the constellation near Perseus. And this represents the speeds of the stars in orbits around the galaxy. And Rubin measured the speeds of stars using ordinary telescopes, and Roberts used radio telescopes to measure the clouds of gas, which essentially can go further out than the stars and give you a much more of a grasp on the speeds of stars further out. And so here then is the sort of result that they found. So here is the galaxy that you see through, when you take an image of the sky, okay? And you find that the speeds of the stars, as you move further out from the galaxy, instead of coming down like this, which is what you expect, because the gravity field should be getting weaker if all the mass is where the stars are, right? In fact, it keeps on rising and gradually levels off, okay, like this. That means there is extra matter throughout the outer part of this galaxy, which is controlling the speeds of those stars. And probably there is up to 10 times more than we actually see. And that was an amazing discovery for one or two nearby galaxies in the 1950s. And since then, we've gone on to make similar conclusions for many, many nearby galaxies. And so this shows you the speeds of stars, what we call the rotation curves, for many nearby galaxies. Each one of these lines is a galaxy. And it just, instead of coming down like this, thousands of light years away from the center where the galaxy seems to end, they just keep on going, okay? Okay, so there is dark matter out there, lots of dark matter. So what does this really mean? We want to check this somehow. We want to see, elsewhere, not just around our galaxy, maybe there's dark matter everywhere. There should be. There's nothing special about the site where we formed. And so let me just now take you to the modern theory of gravity, Einstein's theory of gravity, and try to explain how you would actually really be able to make a map of dark matter. That's what's remarkable about what I'm going to tell you now. Even though it's invisible, we can actually make a map of it, and I want to show you how that's done. So what Einstein said, basically, in his theory of gravity, relativity, is that matter curves space, okay? You can replace matter by space being not Euclidean, slightly curved, so that if you're near a black hole, it's an extreme effect. If you're near the sun, it's a smaller effect. But nevertheless, the three angles of a triangle no longer add up to 180 degrees. As Euclid would have said, space is slightly distorted. And that's from gravity. Okay, and so you can see symbolically how this happens. But at the same time now, light rays have to travel through this curved space. So space also curves light. So these are the two key concepts of Einstein. Matter curves space, and I can replace matter by the curvature of space. But then when I try to observe something, light gets slightly bent, okay? So how do we turn this into something that we can actually go out and measure? And here is the remarkable modern discovery of how you can make maps of dark matter, even though you can't see it directly. Okay, and so this is the way it goes. So here is a distant galaxy. Here is my telescope. In this case, it's the Hubble telescope, but it could be any telescope that can see clearly. And here is, in this case, it's a cluster of galaxies, but full of dark matter. We assume. I'll tell you why we know that in a moment, but we're very confident that this is full of dark matter, as well as ordinary light, but 90% of it's dark matter. So the effect of this dark matter bends space. It also bends the light rays. So the light rays that come from this galaxy pass through and would normally go like this, but they get bent by the curving of space, if you like, by the effect of the gravity, instead of coming, and so this is the way you see part of this galaxy, okay? So some of the light doesn't get bent, comes straight through the center, but the light that goes in this direction feels all this gravity force, okay, from all the dark matter here. So that means that when you look with this telescope at this galaxy, it's the light rays which really come from this distant galaxy seem to come from out here somewhere. So in other words, this galaxy gets turned into, a part of the light gets turned into, basically, if you imagine a circle perpendicular to the screen, a ring. You would see a ring projected on the sky. We call this Einstein's ring because it was essentially a prediction of his theory, if this is true. Okay, so we have now, by taking many, many images, millions of images of galaxies, we find ones that are in the right position to be behind a cloud of dark matter, and we can actually begin to see these rings, which are the manifestation of dark matter. And they tell us, in fact, precisely how much dark matter is in this region, in this case, a galaxy cluster. So before I even get on to galaxy clusters, I'm going to just tell you first about galaxies have lots of dark matter. A cluster is a collection of thousands of them, but let's just focus on the galaxy. So how do we study that? So here is a modern survey that pioneered the way to studying the images and other properties of very distant galaxies. So this telescope, it's a 2.5 meter telescope in New Mexico, funded by the Sloan Foundation, did a sky survey, and it was the first. Prior to that, people had used photographic techniques to map the sky. This is the first one to do it using modern CCDs digitally. And they produced a map of 250 million galaxies and 250 million stars of the whole skies. This is their map. So nearly 500 million points on this, half of which are stars, half of which are galaxies. So we just care about the galaxies. So what you do is you sort through the images of some of these galaxies and you find some really interesting things. And most are just like the normal galaxies, the bread and butter of astronomy that you see typically. But I'm going to show you examples of ones that are Einstein's dream, as it were, namely direct manifestation of the Einstein lens, the Einstein ring of dark matter. So here are 4 examples. So what you have then is this is the ordinary galaxy. In front of it, there is a cloud of dark matter. And the light from, so this is this galaxy has a lot of dark matter in it. So this is the lens, going to be the lens in these 4 cases. And the dark matter around this galaxy is imaging something much, much more distant. So this blue ring comes from a galaxy that's probably twice as far away as this one, okay? And you're seeing the ring of that light being spread out because we're looking at this galaxy more or less down the center, and so the light gets spread symmetrically around it into sort of a ring on the sky. And so here are 4 different examples, and it's obviously, if you don't look at the galaxy, and if the galaxy behind is somewhat irregular, and you don't look at it quite in through the center of this, then you can get slightly asymmetric, this is all of this light is from one galaxy way behind this one, okay? And so that's basically going to tells us there's lots of dark matter. You can even infer how much. And there are some, and so just to remind you again, so again, this is supposed to be this galaxy, and again, it's bending the light, and you're seeing the light from this galaxy now spread out into this ring, which, because of the projection out from the screen, okay, it looks like a ring, as seen by this telescope. Okay, so what I just showed you was the Sloan telescope, but here's the Hubble telescope in space has much better resolution. I mean, from the ground, stars twinkle and all that, the images are rather fuzzy. What you can do from space is really quite amazing. And so this is one of the examples, one of the best ones, of a gravitational lens, okay? And so again, this comes from a distant galaxy. Here is the galaxy, the foreground one, with a halo of dark matter around it, which is lensing the light from one galaxy right behind this one, and it spreads the light out. You can't see the galaxy directly because it's too bright here, but you can see its lensed image, which is this. And you can actually measure this. You show this is all from one galaxy, just one tiny, would be a tiny dot on the screen like this maybe, were it not for the fact there's a galaxy right in front of it. Okay, so, this is dark matter as directly imaged effectively, and I'll show you how we can turn this into a map in a second. But let's go back to the historical beginning of this. So in 1933, astronomer Fritz Zwicky, he's the first one who proposed that there was dark matter. And he wrote this in German. He was based in Switzerland at the time, before he moved to Pasadena, Das dunkle Material. And his logic was that he was an expert on clusters of galaxies. They're collections of hundreds or thousands of galaxies in the sky, and he was able, using astronomy techniques, especially using the Doppler shift of light, to measure the speeds of all the different galaxies. And he realized that they would fly apart, given the measured speeds, unless there was some big cloud of dark matter, which probably had to weigh 5 or 10 times as much as the mass in the stars that he could see in those galaxies. And so he then proposed dark matter in this paper. But it was a conjecture, and the conjecture stayed there for a very long time until gravitational lensing took over. And so this is the way that gravitational lensing works for the cluster of galaxies. In fact, this is the very one that he studied in his earlier paper. So all of these are galaxies in this cluster. And if you look now carefully at the images of these galaxies, you find that because of there are some very faint ones in the field that are behind this cluster. So the bright ones are in the cluster, the fainter ones are way behind. If you look at the images of the faint ones, you find they're very slightly distorted. They're like arcs, they're bits of arcs that would ordinarily be a whole ring if you looked at them exactly center on, but you don't, so you get distortions. Okay, so what one does is one makes a map of those distortions, and this is the map that you get. So this is the promised map of dark matter. The first map we have, which is directly that of the dark matter that you can't see directly in this galaxy cluster. So and let me now show you a close-up of one of the clusters that does this. So here's an example of such a galaxy cluster. And you can see now, and all these things, these weird shapes, these arc-like shapes, are from background galaxies. There are a number of them now. There's no single one that's right behind the center of the cluster. And it's complicated because each of the galaxies in this foreground cluster has its own cloud of dark matter. And all of that stuff, the individual galaxies plus the whole cluster, are lensing the background. So nevertheless, if you look at all these, so here we have one giant arc probably, this may be one galaxy, but all these other images are slightly distorted, and the net effect is you can make a map of the dark matter. Okay, so the cluster of galaxies has is a laboratory of dark matter, full of dark matter. Here's another example of a galaxy cluster. Where you can see, so this is one distant galaxy behind the cluster, okay? So the dark matter in this entire cluster is imaging one background galaxy to give you this enormous arc, okay? And many of these other weirder things are other galaxies, but you can, so these are all distorted galaxies by the dark matter. Here's another galaxy, arc further out, and so on. And so all of these things are testimony to dark matter. So just to give you some feeling for why this is a simulation of a cluster of galaxies just passing it across the background. So it's just moving through the background, okay? And you can see how, the galaxies right behind give you these beautiful arcs, but everything gets distorted. Everything that comes behind this cluster gets some weird distortion. So this is just the effect of gravity. It's a transparent lens. Gravity is bending light. That's what we're seeing. Okay, that's just. So this is a great manifestation of the dark side of the universe that we can't see directly, but we can see its consequences. But it doesn't stop there. So here's another remarkable thing. Okay, so here again, I'm showing you, here's a galaxy with dark matter, okay, and the light is being bent, okay, as it comes from this background object past the galaxy. So the light from here gets bent, okay? And so the interesting thing is that if I now imagine different light rays, okay, it turns out that this one galaxy, which is being lensed by this, if it's not exactly in the center, is going to give you more than one image. You see, here is the same galaxy as seen by looking in this direction. You don't know the light's being bent, so you just follow the light rays. You see an image here. And here, if you look in another direction, you also see an image there as well. So typically, this ordinarily will be part of some giant ring, okay? But because it's not exactly center on, you're seeing different images, okay? So if things are, and so the typical thing you expect is multiple images of the same object, okay? So it's as though things are multiplying in front of you. And we've actually measured this. So here's an example, okay, of the same object, okay? Here is a quasar, a very compact, very distant, very massive object, way behind this galaxy, and it's produced 4 different images. These are the same object. How do you know they're the same object? You take the spectrum of each of these objects, you prove it's the same. So things are multiplying in front of us. It's really, the phenomenon is remarkable. And here's another object. Again, galaxy, lots of dark matter, a quasar right behind it that you can't see directly very easily. And these are the 4 images, in this case, of this quasar, all the same object, okay? Again, proof that gravity is basically enabling you to measure dark matter. Okay, so, and it doesn't stop there. So here is one of the most amazing consequences, just an experiment just done last year of this same phenomenon. So again, imagine now a galaxy back here somewhere, and here's our telescope. And again, light is being bent by the gravity field in this cluster. So what I want you to notice, though, is that in this case, these different bent images have different lengths, okay? So the image that gets bent like this, okay, light will take a bit longer to get here than it does from this one, okay? So that means there should be a time delay, okay? So here is the amazing example. So in this example, they saw an explosion, a supernova, an exploding star go off in the galaxy, which they measured in one of, directly with the telescope. They saw that happen. But because of this model, they were able to predict there should be a light path with a longer passage time. Therefore, last October, they said, well, let's look, and we should expect to see the same star exploding that we already saw last year, the year before, and there it was. They found it in December. Difficult to see, but they predicted there would be an explosion, and they saw that explosion because they'd already seen it before. So it's as though you can predict the future. It's really amazing because of the complexity of gravity. So that's, the way we can now be totally confident that we live in a universe where galaxies and clusters of galaxies, the collections of galaxies, have vast amounts of dark matter. Okay, so let's for a moment just go back to the roots of all of this in cosmology. So in some sense, we can now measure dark matter throughout the universe because, every time you look behind a galaxy, you can sample the dark matter and you can get some feeling for where it is more generally, because everywhere you look, there'll be tiny distortions. And this is a map of those distortions in some random place in the sky. Okay, hard to see. It's a small effect, but we're convinced that this is basically a pure dark matter map of a patch of the sky. Now, this map was produced for a universe in which there's lots of dark matter, a universe that will have so much dark matter that in the future it will eventually stop expanding and collapse again, okay? So if I now show you another universe, this is all done on a computer, a simulation, this numerical simulation. Here's a universe in which there's just 1/3 of this density of dark matter. That universe, in principle, would expand forever, okay? Then you can see the map is different. So by studying the details of the distortions of the galaxies, you can actually measure the future of the universe, determine the future of the universe, and decide how much dark matter there will be, apart from the minor problem of dark energy, which is another issue, but that complicates things. But nevertheless, you can tell how much dark matter there is in the universe by comparing these two maps, because it's dark matter that gives you these different distortion patterns. So this is less distorted than this. There's more dark matter on the left, less on the right. You can sort of figure out the pattern with the aid of a computer. Okay, so we conclude that our universe looks like this. Okay, it's only 1/3 this so-called critical density of dark matter. That's our universe. Okay, now I want to move on to try to say some things about what is this mysterious dark matter. And so this is a really big challenge for astronomy and for physics, because it's one thing now to show you the maps that we have. We know the dark matter's there, but what is it? And we'll never be satisfied till we've identified it. So your first assumption is that it might be just made of ordinary matter that's dark, black holes or something, whatever, okay? Just dark clouds, And so that's something that you can study in detail, because ordinary matter, whatever form it's in, does emit light, does affect things, at some level. Even black holes accrete stuff and glow, okay, whatever, okay? And we can be pretty sure that the dark matter cannot be ordinary matter. We have to move to something more exotic. Here is one example of something more exotic. When I gave a talk in Australia some years ago, this got into the newspaper. I was going to talk about the possibility the dark matter was made of ordinary stuff, baryonic dark matter, and the newspaper columnist wrote at least 90% of the mass of the university is in the form of non-luminous matter. Okay, right. So that probably is true, actually, but it's not. It's not the topic of this talk, right? So anyway, so here is an example of why we're sure that dark matter is something incredibly weakly interacting. I mean, the matter that we're made of interacts, it glows, etc. But we think dark matter is practically invisible. I'll explain how we can try to see it. And so here's an example where you can see in this galaxy cluster, by using an X-ray telescope, they could conclude that this is where the hot gas, most of the mass of the cluster is here. Okay, that's this cloud over here. And by using this gravitational lensing technique, okay, they discovered there was lots of dark matter over here and over here, telling you that as this probably formed by the merging of two clusters, and they obviously went through each other like ghosts in the night, as it were, okay? And so the dark matter clouds emerged on either side, and the atomic matter sort of got compacted and compressed and lost energy and stayed in the center. So this tells you that the dark matter really does move like a ghost through ordinary matter. This is a direct observational confirmation of the fact, apart also from the obvious thing that because the dark matter is outside where the stars are, it obviously cannot have collapsed and made the stars. Right? That's what we see, therefore also it must be, a very, very weak interaction. So that's why we're so sure. This is a graphic example of how that works. And we say that dark matter intrinsically must be very, very weak interacting, and therefore very hard to observe with our telescopes or with any experiments. Okay, so how do we go about doing this? Okay. So let me just take you through, this has been something of great interest to the physics community, and so let me just give you the physics perspective on the dark matter. So one of the underlying themes of our understanding of elementary particles, and I'll show you examples of recent discoveries in a moment, is that at some incredibly high energy, they were all the same. I mean, we're made of protons and electrons, big ones and lighter ones, other things too, but they're very different today. But in the very, very early universe, we believe that things were unified at sufficiently high energy. Now, we try to approach high energy in particle accelerators, like the Large Hadron Collider at Geneva, but we can't get nearly high enough energy to produce unification, but we believe that in the very early universe, that was the ideal state because there are enormous energies present naturally at the beginning of the universe in the Big Bang. And so the universe was then very hot, and then all these particles were presumably present, and this theory of unification, we call it supersymmetry, SUSY for short. It unites everything together at a temperature which is enormous compared to the mass of a particle. Basically, you take the mass of a particle, Einstein's famous equation, mc squared, and that gives you some incredibly high temperature equivalent. And when the universe was a millionth of a second old or less, so we're extrapolating back to this time. And then if this theory, which we believe should be correct, no one knows for sure, we're trying to test it, but the prediction of this idea of unification is that all known particles have some partner from this super theory, super partners we call them, and they're all totally unstable. They all collapse so we never see them, they're not around today, except for the lightest one, which is stable in this other sector of matter of the universe. And that, we say, my colleagues tell me, is the best candidate we have for dark matter, because not only is it predicted by the most fundamental theory we have at the beginning of the universe, this theory of supersymmetry, but also it turns out to give you roughly the right amount to actually explain the dark matter. So it's a very nice coincidence, and so that encourages one to try to look for it. So how on earth can you look for this particle, which by definition is almost impossible to see, okay? So we have a name. To start with, we give it a name, okay? So the name we give it is weakly interacting massive particle, or WIMP for short. Okay? And so our first thought is this, that these WIMPs, which are the particles of dark matter, are passing, they interact, they're passing through us. Through our bodies, there are millions every second that are, and we don't know it. They don't do anything. They don't cause any radioactivity or anything. Okay. But they do every now and then very rarely interact. Very, very rarely. Okay. And so how on earth can you try to cope with that? Well, you devise experiments, okay, that are designed to look for very, very rare events, dark matter collisions with your detector. You have to go to a highly shielded environment, because cosmic rays, which bombard the Earth from space, can give you very similar signals to a dark matter particle hitting something, which rarely gives a glow. But every now and then they will interact, they will scatter very, very weakly, but if I have enough detector there, I'll get a rare flash of light from one of these scatterings, and maybe I can see something. And you look for effects in your detector. It might be scintillation of some crystal, or a bit of heat that's given by this dark matter particle, or maybe you can ionize some material. So these are different techniques we use. Okay, so what do we do? Where do we go to do these experiments? Okay, so this is the first criterion is you have to go very, very deep underground. So this is a region in Italy, in an area called Gran Sasso, in a mountain range in the north of Italy, and there's a railway, there's a road tunnel that goes under that mountain, with 1,000 kilometers, a kilometer of rock or more above it. Okay, so you're shielded by all this rock, and in this tunnel they've excavated large laboratories to try to study dark matter. And so in these laboratories, one has now installed these massive detectors, which are now shielded from cosmic rays to look for dark matter. So I'm going to show you examples of some of these in a moment. The bottom line is that we have not found the dark matter yet, except there is one experiment that's been running for nearly 15 years now that has claimed to see something, a signal. So let me tell you how that works, because if it were right, it's amazing. It probably isn't, but so this is what this experiment does, led by Rita Bernabe in the University of Rome. And so imagine, as the Earth goes around the sun, so there's this dark matter out here, and because we're moving, the sun is moving around the galaxy, okay, it's like you see a wind of dark matter crossing you because of our motion relative to, this dark matter in the halo around us. And this wind of dark matter means that because you occasionally get some scatterings of the dark matter in your detector material, which in this case turns out to be sodium iodide crystals, you expect to see a slight change over the course of the year as you go into the wind or out of the wind. Okay, there should be a slight maximum, slight minimum. It's a modulation of order a few percent, and they claim so every year that goes by in June they should see a maximum, in December a minimum, and so you can see the error bars were huge at the beginning. These are uncertainties of experiment, but over the more recent years, as the experiment got more precise, you can see they're seeing this up and down, which they claim is proof of this wind of dark matter, therefore evidence for the dark matter. They're picking out this very, very weak signal by looking for the modulation up and down, of course, of this wind. So that was their idea, okay? And this was like a red flag because many people were skeptical of this result because they had some sort of proprietary approach to their experiment. They never released the raw data. And so many experiments around the world realized this was the prime target for them, and they began the chase to try to confirm them or reject them. And so here's one experiment. This is in the Black Hills of South Dakota in a gold mine, former gold mine, stopped operation, 1 mile underground now, okay? One sets up an experiment, okay, full of, in this case, liquid xenon, okay? It's a heavy material. The idea is you think your dark matter particle might be a heavy particle, and so you get optimal scattering if the mass of the particle matches the mass of your detector particle. And so this experiment, led by this guy, you can see the cavity where they set it up. And they've managed to set these are upper limits. This represents limits on the cross-section. And in this inset, you can see where the Rome experiment was, and their limits are now much lower, suggesting that the Rome experiment just, for some reason, and I'll give you some thoughts why that might be in a second, was not finding dark matter, but something else. And it's not just their experiment. Here's another one, which is under construction, just beginning to operate now in the Gran Sasso lab, the same place that I showed you where they measured the modulation. And that's under this 1.4 kilometers of rock inside this freeway. And so they also have established their own detector. And likewise, they're not finding any dark matter either. And again, this is an interesting way to show it. This is where the original experiment would be, and they're way, way below this in their limits. Okay, so this has become a major activity around the world. Look at this. So these are all experiments in mines or under mountains all over the place. We have Japan, I'll show you more of that in a moment. Gran Sasso, which I showed you in England, Bowlby in Yorkshire, we have our own national experiments up there. In Canada, in the US, there are a couple, and so on. And even at the South Pole, there's a new one being constructed deep under the ice. So some of these are very deep indeed. The deepest one is the Chinese experiment, which is goes down some 2.5 kilometers. So the depth is important because the deeper you are, the more shielded you are from false signals that might give you some contamination. Over the course of the year, you worry that the rock does change, its radioactive emissions very, very weak, very, very slightly. And so that could be the seasonal variation, could be due to something in the rock as opposed that was reported before or something. So the deeper you go, the safer you are from. So here is a little close-up on the Chinese experiment. And they're using another technique, using germanium. And they're under this mountain again. A freeway goes through it. They've built this big lab, and they basically are celebrating here when the tunnel was opened a few years ago, and they've recently installed again a huge detector with liquid xenon. And so the aim is now to go on and build bigger and bigger detectors. Okay, and these are 1-ton detectors we have now, and the aim will be eventually to build them up to 100 tons in the future. So there's almost to try to definitively either find dark matter or reject it. It's got to be there somewhere, we think, and so the bigger the detector, you hope. Okay, so that's the brute force way, you might say. We want to actually get a bit of dark matter in our hands, as it were, by seeing it in our detector. Okay, so there is another way. And that is to look in an atom smashing machine. Okay, and the idea is you smash 2 protons together at great speed, and eventually you might produce a particle of dark matter, because this is how it began in the early universe. Dark matter particles were produced naturally then, and now and today in the accelerator you can't get up to high enough energy, but that does mean very, very rarely there's a small chance you'll make something. So where do we go to try to make dark matter? So this is the place that we go to. This is the Large Hadron Collider in Geneva. This is a tunnel 27 kilometers in diameter under the ground, and one sends a beam of protons at very, very high energy one way, and then another beam the other way, and they collide together in areas where you put masses of detectors to look for light flashes, because particles do, when they collide, give you a spray of high-energy X-rays and other things, which you can see with various detectors, and you look for traces of something really, really unusual, okay, which might be a clue as to what the dark matter is. So basically, the way that works is that in some high-energy collision, you create lots of known particles, but energy is conserved, right? We know fundamentally for every particle that goes one way, there's another that goes some other way, and the energy must balance out. But if, for example, you see a beam of particles coming off one side and nothing on the other to match it, you say, aha, that might be dark matter, because something is coming off that's carrying the energy, but we can't see it. So that's the sort of thing we try to look for in these accelerators. So let me take you now towards, so this is the tunnel, 27 kilometers long, with this enormous tube in which you're sending these very high energy particles. This is a close-up. This is a person back there, so you can see it's of one of these tunnels. And then at different places around this tube, you have an enormous area where you can look for these light flashes. So this is, when they were constructing this was taken before they closed off the tunnel. So this is a huge lab. Imagine the complexity of all the cabling and all of this. All of these are light detectors, which are going to be looking for flashes of light. And this is a close-up of getting into this, okay? Okay, and so these are two major detectors at the Large Hadron Collider in Geneva, okay? Okay, so they made a major discovery a couple of years ago, which got into the headlines. Their primary goal was not to look for dark matter. It's one of their goals, but their primary goal was to look for the missing bit from the standard model of particle physics, which we call the Higgs boson, okay? Discovered by Peter Higgs, among others, who got the Nobel Prize for that. Peter Higgs from Glasgow, okay. Anyway, so here is the discovery by these 2 detectors of this. So these are various events that they see, and they look for signals. That these curved lines are events. They photograph basically with their detectors, and they look for things spraying off from the collision. And so you have enormous amounts of debris. And now, one has discovered that the Higgs particle. That's great. And now the next step is to try to see if there's something invisible occurring that would be your most direct way you could produce the dark matter. So they haven't found it yet. But There's enormous hope. There's a lot of excitement. They had to turn off, they're running now, they had to turn off this experiment over Christmas because it takes so much electricity to run that it would be 1/3 the power to run the city of Geneva. So they can't afford it, basically. So they closed down for 3 months. They're just beginning to reopen. And there are curious signals that are coming out. Everyone in the particle community is holding their breath, waiting to see what happens. If the tantalizing signals get reinforced or not, we'll know probably in 6 months. So there's, so who knows? They may or may not be on the verge of discovery. We have no idea. But it's an exciting time in particle physics because of this amazing experiment. Okay, so let me take you on to one more step in this. And this now is using astronomy to look for dark matter. And so every now and then, the dark matter particles out there around us hit each other. And when they hit each other, the theory says they have this curious property. They should self-annihilate, self-destruct. And when they self-destruct, these are particles that are much more massive than protons. They will produce tiny flashes of light. And not just, and the light will be gamma rays, but also maybe neutrinos, very difficult particles to see, but fundamental particles, very, very light, but can be detected, and positive electrons. They're, again, very rare normally in space. So to run you through some of these experiments, again, which are giving tantalizing hints but no signal whatsoever, let's look at one detector, okay? So this is the sun. As seen in X-rays. So the sun is actually a collector of dark matter. As the sun goes around the galaxy, dark matter particles fall into it. And and those dark matter particles, when they hit each other, they collect in the center of the sun, they give you these neutrinos, which are ghost-like particles with very high energy. And those ghost-like particles of high energy can occasionally get to the Earth. So imagine this weird stuff going on in the middle of the sun, which theory says must happen. They hit the Earth, then in the Earth, they will be trapped in the inside of the Earth, and there they will produce other particles which are unstable and can give flashes of light. And so we now have experiments looking for these light flashes. And so one experiment is at the South Pole and consists of sending strings of phototubes, drilling in the ice with very hot water, steam basically, and down to enormous depths, and looking for flashes of light that come from some random direction. And because they come from different parts of the Earth, they have different delay times, you use triangulation to figure out where they come from. And so that's one experiment at the South Pole. Another one can use ice because it's transparent, you can see light flashes. Another one uses water. And again, in the water, this is in the Mediterranean off the coast of Toulon, you have to go very deep down to the seabed. These lines are laid by mini submarines. And again, you're looking over a kilometer or so, strings of these phototubes for light flashes coming from down below, from these weird particles from the sun hitting the Earth and giving you light flashes. So that's all rather remarkable. Okay, but nothing has been seen yet, but it's experiments that are going on. Okay, I mentioned light. I talked about gamma rays maybe. I'll come to that again in a second. That was neutrinos. What about these weird things called positrons, positive electrons? They're very, very rare in space. So here's an experiment that was set up a few years ago, very recently actually, 3 years ago, on the space station. So this is the International Space Station orbiting the Earth, okay? And on it we have a cosmic ray detector called AMSO2, and it is designed to look for dark matter, for these really high energy particles, positive electrons, that are produced when dark matter particles annihilate. And you expect them in the cosmic rays, but the amazing thing that's been found by this experiment is that here is the cosmic ray contribution, but when they look at the positrons, these come along with the electrons as part of the cosmic ray debris, but they find at high energy this increasing amount, okay? So here's another way to look at it. So what you expect from cosmic rays is the positrons should just keep on going down. You run out, okay? But in fact, they find a new component, and they have millions and millions of events. So this is a mystery, and one of the theories is this might be the dark matter, but that's not the only theory. Another theory is that it these positrons are produced by astrophysical sources, which are known to produce positrons, and it could be just that, coming in at very high energy. We just don't know for sure. Okay, that's another mystery. Let's just move on now to the final thing, which are the gamma rays. And this is a simulation of the galaxy forming from dark matter only. And what you should notice is this is our dark halo. So this is one of the amazing things we've learned from doing simulations, that all the dark stuff around us is not some giant amorphous blob, but full of these clumps of dark matter. And because there are these clumps of dark matter and a huge concentration in the middle, there's a chance that it's dense enough where these annihilations of dark matter particles occur for some of the gamma rays to escape into space and glow. And so we have a telescope that's been looking for this, again, for a few years. It's been in space looking for other stuff too. So it's orbiting the Earth. It's a gamma ray telescope, and it's produced the following map. Okay, and so this is a map of the gamma ray sky, and hiding inside this map, and these are sources of gamma rays. This is diffuse emission from the Milky Way, but hiding inside, especially where the dark matter concentrates, we think there might be an invisible glow of dark matter. Okay, and this again got very exciting a few years ago. I'll just show you one evidence of this glow. So this is a microwave map of the sky made by an early satellite. Okay, and so behind, and this is all dust, this is the Milky Way. Behind the dust, one saw this mysterious glow, okay, which could have been due to dark matter lighting up. Okay, but since then we've discovered the following, that what's going on in and this is the whole story of how hard it is to find dark matter. So we've since found that, there probably was an enormous explosion a long time ago, and there's this huge glowing gamma rays found by the Fermi satellite, so it's not dark matter at all. Okay, so let me try to, that's a shame. Hopes come and go. It was excitement for a while, but now it's gone away. Another great laboratory for dark matter are these. These are the faintest possible galaxies that we know about, just patches of light which you can barely see, and we believe they're full of dark matter. We've looked at them in detail with these satellites. We've found nothing at all. We're now building many futuristic experiments for these things. These are arrays of detectors in Utah. This one's in Namibia. This one is in space. This is a Chinese satellite just launched in December, underground things. All of these designed to carry us forward on the dark matter push. And so what about in the future? Where are we going to go? Again, we're going to build, just recently approved, to be finished in 3 years' time, a huge array of telescopes designed to look for flashes of gamma rays in the sky, one in the Atacama Desert, one on La Palma, north and south. And then here we have amazing telescopes being designed. This one was just launched in December by the Chinese. This one is being planned by the Russians, all to look for gamma rays. And then finally, we have our neutrino telescopes. I showed you these two already. And here is the most incredible one of all, which is being built and being upgraded. So here we have some 60,000 tons of highly purified water. And you have technicians on a little raft over here going around. All these are phototubes, again, looking for these tiny, tiny light flashes that are manifestations of originally from dark matter, who produce neutrinos that get trapped in these detectors by producing these other particles on the way through the Earth. Okay, and they're going to upgrade this in the next few years, to 1 million tons of water, and that'll be in 10 years' time. So this is a Japanese experiment called Hyper-Kamiokande, inside a mine, at the bottom of a mine. Okay, so to summarize, dark matter's here to stay. We don't know what it is. Many, many experiments worldwide. In a decade, we'd better find it, or else we'll need to change our theory. So, thank you.